Contemporary geometry. Euclidean geometry. Euclidean geometry is geometry in its classical sense, as it models the space of the physical world. It is used in many scientific areas such as mechanics, astronomy, crystallography, and many technical fields such as engineering, architecture, geodesy, and aerodynamics and navigation. The the mandatory educational curriculum of the majority of nations includes the study of Euclidean concepts such as points, lines, planes, angles, triangles, congruence, similarity, solid figures, circles, and analytic geometry. Euclidean vectors. Euclidean vectors are used for a myriad of applications in physics and engineering, such as position, displacement, deformation, velocity, acceleration, force, etc. Differential geometry. Differential geometry uses techniques of calculus and linear algebra to study problems in geometry. It has applications in physics, econometrics, and bioinformatics, amongst others. In particular, differential geometry is of importance to mathematical physics due to Albert Einstein's general relativity postulation that the universe is curved. Differential geometry can either be intrinsic, meaning that the spaces it considers are smooth manifolds whose geometric structure is governed by Riemannian metric, which determines how distances are measured near each point, or extrinsic, where the object under study is a part of some ambient flat Euclidean space. Non-Euclidean geometry. In mathematics, non-Euclidean geometry consists of two geometries based on axioms closely related to those that specify Euclidean geometry. As Euclidean geometry lies at the intersection of metric geometry and affine geometry. Non-Euclidean geometry arises by either replacing the parallel postulate with an alternative or relaxing the metric requirement. In the former case, one obtains hyperbolic geometry and elliptic geometry, the traditional non-Euclidean geometries. When the metric requirement is relaxed, then there are affine planes associated with the planar algebras, which give rise to kinematic geometries that have also been called non-Euclidean geometry. Topology. Topology is the field concerned with the properties of continuous mappings and can be considered a generalization of Euclidean geometry. In practice, topology often means dealing with large-scale properties of spaces such as connectedness and compactness. The field of topology, which saw massive development in the 20th century, is in a technical sense a type of transformation geometry, in which transformations are homomorphisms. This has often been expressed in the form of the saying topology is rubber sheet geometry. Subfields of topology includes geometric topology, differential topology, algebraic topology, and general topology. Algebraic geometry. Algebraic geometry is fundamentally the study by means of algebraic methods of some geometrical shapes, called algebraic sets, and defined as common zeros of multivariate polynomials. Algebraic geometry became an autonomous subfield of geometry, 1900, with a theorem called Hilbert's nullsentence that establishes a strong correspondence between algebraic sets and ideals of polynomial rings. This led to a parallel development of algebraic geometry and its algebraic counterpart called commutative algebra. From the late 1950s through the mid 1970s, algebraic geometry had undergone major foundational development with the introduction by Alexander Grothendieck of Scheme theory, which allows using topological methods, including cohomology theories, in a purely algebraic context. Scheme theory allowed to solve many difficult problems not only in geometry but also in number theory. Will's proof of Fermat-Last theorem is a famous example of a long-standing problem of number theory, whose solution uses Scheme theory and its extensions such as stack theory. One of 7 Millennium Prize problems, the Hodge conjecture, is a question in algebraic geometry. Algebraic geometry has applications in many areas, including cryptography and string theory. Complex geometry. Complex geometry studies the nature of geometric structures modeled on, or arising out of, the complex plane. Complex geometry lies at the intersection of differential geometry, algebraic geometry, and analysis of several complex variables, and has found applications to string theory and mirror symmetry. Complex geometry first appeared as a distinct area of study in the work of Bernhard Riemann in his study of Riemann surfaces. Work in the spirit of Riemann was carried out by the Italian school of algebraic geometry in the early 1900s. Contemporary treatment of complex geometry began with the work of Jean-Pierre Serre, who introduced the concept of sheaves to the subject and illuminated the relations between complex geometry and algebraic geometry. The primary objects of study in complex geometry are complex manifolds, complex algebraic varieties, and complex analytic varieties, and holomorphic vector bundles and coherent sheaves over these spaces. Special examples of spaces studied in complex geometry include Riemann surfaces and Calabi U manifolds, and these spaces find uses in string theory. In particular, world sheets of strings are modeled by Riemann surfaces, and superstring theory predicts that the extra 6 dimensions of 10-dimensional spacetime may be modeled by Calabi U manifolds. Discrete geometry. Discrete geometry is a subject that has close connections with convex geometry. It is concerned mainly with questions of relative position of simple geometric objects, such as points, lines, and circles. Examples include the study of sphere packings, triangulations, the Kneser-Poisson conjecture, etc. It shares many methods and principles with combinatorics. Computational geometry. Computational geometry deals with algorithms and their implementations for manipulating geometrical objects. Important problems historically have included the traveling salesman problem, minimum spanning trees, hidden line removal, and linear programming. Although being a young area of geometry, it has many applications in computer vision, image processing, computer-aided design, medical imaging, etc. Geometric group theory. Groups have been understood as geometric objects since Klein Erlangen programming. Geometric group theory studies group actions on objects that are regarded as geometric, specifically Isometric actions on metric spaces to study finitely generated groups, often involving large scale geometric techniques, and borrowing from topology, geometry, dynamics, and analysis. It had a significant impact on low dimensional topology and celebrated result from Agol's proof of the virtually Haken conjecture that combines Perelman geometrization with cubulation techniques. Group actions on their Cayley graphs are foundational examples of isometric group actions. Other major topics include quasi-isometries, Gromov hyperbolic groups, and their generalizations, relatively and excellently hyperbolic groups, free groups, and their automorphisms, groups acting on trees, various notions of non-positive curvature for groups, cat groups, Dean functions, automaticity, right-angled Artin groups, and topics close to combinatorial group theory, such as small cancellation theory and algorithmic problems, e.g., the word conjugacy and isomorphism problems. Other group theoretic topics like mapping class groups, property, solvability, amenability, lattices, and line groups are sometimes regarded as strongly geometric as well. Convex geometry. Convex geometry investigates convex shapes in the Euclidean space and its more abstract analogies, often using techniques of real analysis and discrete mathematics. It has close connections to convex analysis, optimization, and functional analysis, and important applications in number theory. Convex geometry dates back to antiquity. Archimedes gave the first known precise definition of convexity. The isoperimetric problem and recurring concepts in convex geometry was studied by the Greeks as well, including Zenodorus, Archimedes, Plato, Euclid, and later Kepler and Conexter all studied convex polytopes and their properties. From the 19th century on, mathematicians have studied other areas of convex mathematics, including higher dimensional polytopes, volume, and surface area of convex bodies, Gaussian curvature algorithms, Tillings, and lattices.